Tonight, we are going to spend some time with something that surrounds everything. Something so vast, so pervasive, and so thoroughly misunderstood that most of us have never stopped to question it. We are going to look at empty space, not the planets, not the stars, not the clouds of gas and dust that drift between them. We are going to look at the space between all of those things, the dark, silent regions that appear, at first glance, to contain absolutely nothing at all, and we are going to find that they do not. For most of human history, empty space was treated as absence, a backdrop, a passive emptiness in which matter simply happened to exist. The vacuum was nothing more than a container, featureless, inert, and of no particular interest to anyone. But over the last century, physics has uncovered something far stranger. What appears empty is not truly still. Even in complete darkness, even in regions stripped of particles and light, something remains. Something that cannot be removed, cannot be quieted, and cannot be explained away. This video will take you through the nature of the quantum vacuum, the invisible fields that fill all of space, the strange restlessness that persists even at the coldest temperatures the universe permits, and what all of this tells us about the fabric of reality itself. We will move slowly. There is no hurry here. Each idea will have room to settle before we move to the next. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Let's begin. Chapter 1. The idea of nothing. The word nothing is one of the oldest words in any language, and one of the most difficult to hold in the mind for long. We use it casually. We say there is nothing in a room, nothing in a jar, nothing between two distant points. But when philosophers and scientists have tried to define nothing with precision, to describe what a true and complete absence would actually look like, the concept has had a way of resisting them. The ancient Greeks were among the first to wrestle seriously with the idea of empty space. For many of them, the very notion of a void was considered philosophically impossible. Aristotle argued that a true vacuum could not exist in nature. His reasoning was rooted in the physics of his time. If empty space contained nothing, then there was nothing to resist motion, and without resistance, an object placed in a vacuum would move infinitely fast. Since infinite speed seemed absurd to him, he concluded that the vacuum itself must be absurd. Space, in his view, was always filled with something, even if that something was invisible. This was not a fringe position. It shaped scientific thinking for nearly 2,000 years. The idea that nature abhors a vacuum became something close to a principle, repeated and accepted across centuries of natural philosophy. Emptiness was treated not as a physical reality, but as a logical impossibility, a concept that collapsed under scrutiny. It was not until the 17th century that experiments began to push back against this view. In 1644, the Italian physicist Evangelista Torricelli created what may have been the first laboratory vacuum, using a column of mercury in a glass tube. When the mercury fell, it left behind a sealed space at the top of the tube that appeared to contain nothing at all. That space, still known today as the Torricelli vacuum, became one of the most debated objects in early modern science. Some insisted it must still contain something subtle and invisible. Others accepted it as genuine emptiness. The debate continued for generations. As the tools of physics grew more refined, the question of what truly occupied empty space became more urgent, not less. Each time scientists thought they had accounted for everything in a region of space, something else turned up. Light, it turned out, did not need a medium to travel through. Gravity reached across apparently empty distances without any visible carrier. And eventually, in the 20th century, physicists discovered that what they had been calling empty space was not empty in any meaningful sense at all. This was not a minor revision to the picture. It was a fundamental one. The vacuum, that ancient symbol of absence, the thing Aristotle said could not exist, turned out to be one of the most active and structured environments in the known universe. Understanding how physicists arrived at that conclusion and what they found when they got there is where this journey begins. We start with nothing, and we find slowly that nothing was never really there. Chapter 2. The Ether and the Void. For most of the 19th century, physicists believed that empty space was not empty at all, and they had what seemed like a perfectly reasonable explanation for why. Light, they knew, was a wave, and waves, as far as anyone could tell, required a medium to travel through. Sound moves through air. Ocean waves move through water. It followed, quite naturally, that light must move through something as well. That something was given a name, the luminiferous ether. The ether was imagined as a substance of extraordinary properties. It had to be perfectly transparent, since light passed through it without any visible distortion. It had to be present everywhere, since light reached us from the most distant points in the universe. It had to be rigid enough to carry waves moving at the enormous speed of light, yet somehow offer no resistance whatsoever to the planets and moons moving through it. It was, in short, a substance that had to exist, that everything depended on, and that nobody could detect, measure, touch, or describe in any physically satisfying way. This did not stop scientists from trying. For decades, physicists worked to incorporate the ether into their models of the universe, assigning it properties as needed whenever the existing description fell short. When new observations failed to fit the theory, the ether was adjusted. When experiments produced unexpected results, the ether was modified. It became, over time, less a discovered feature of nature and more a placeholder, a way of preserving the assumption that space must be filled with something, because the alternatives seemed too philosophically uncomfortable to accept. The most direct challenge came in 1887, when the American physicists Albert Michelson and Edward Morley designed an experiment specifically intended to detect the Earth's motion through the ether. Their reasoning was careful and precise. If the ether was stationary and the Earth was moving through it, then light traveling in the direction of that motion should arrive at a detector at a slightly different time than light traveling at right angles to it. The difference would be extremely small, but their instrument, an interferometer of remarkable sensitivity, was designed to measure exactly that kind of difference. They ran the experiment. They checked it. They ran it again at different times of year, when the Earth was moving in different directions through its orbit. In every case, the result was the same. There was no difference. Light moved at the same speed in every direction, under every condition they could arrange. The ether, if it existed, was producing no measurable effect on anything. The Michelson-Morley experiment became one of the most important null results in the history of science. It did not confirm what it set out to find. Instead, it quietly dismantled one of the central assumptions of 19th century physics. The ether concept limped on for another decade or two, patched and modified by various theorists attempting to save it, but the damage was done. When Albert Einstein published his special theory of relativity in 1905, the ether became unnecessary. Einstein's framework did not require light to travel through any medium at all. The speed of light was not a property of what filled space. It was a fundamental constant of the universe. the same for every observer regardless of their motion. Space itself could be genuinely empty, and light would still move through it at the same speed, in all directions always. For a brief period, the picture seemed to resolve into something clean and satisfying. Matter existed. Space was the absence of matter. Light crossed that emptiness at a fixed speed. The old confusion about what filled the void appeared to be over, but the resolution did not hold. Even as relativity was reshaping the understanding of space and time at large scales, a separate and equally profound revolution was gathering momentum at the other end of the psi spectrum. Physicists studying the behavior of atoms, electrons, and light at the smallest measurable scales were finding that nature at that level did not behave the way classical physics predicted. Particles did not follow smooth paths. Energy did not vary continuously. The properties of matter at tiny scales were jumpy, probabilistic, and deeply strange. Quantum mechanics, developing rapidly through the 1920s, offered a new mathematical framework for describing this strangeness. It was extraordinarily successful, more accurate in its predictions than any theory that had come before it. But it came with a cost. The picture of reality it implied was deeply unsettling. At the smallest scales, nothing was ever fully at rest. Nothing was ever perfectly defined. And the space between particles, the space that had seemed, for a moment, to be genuinely and peacefully empty, turned out to be anything but. The equations of quantum mechanics, when applied to empty space, produced a result that theorists initially struggled to interpret. Even in a region containing no particles, no radiation, and no measurable energy of any kind, the mathematics insisted that something was still happening. The vacuum was not quiet. It was not still. It possessed a kind of baseline activity that could not be subtracted away, could not be set to zero, and could not be made to disappear regardless of how the calculation was arranged. The ether had been wrong, but the idea that empty space was a passive, featureless void was about to be proven equally wrong, in ways that were stranger, and in some respects more unsettling, than anything the ether theorists had ever imagined. Chapter 3: The Uncertainty Principle. To understand why empty space cannot be truly empty, it helps to spend a little time with one of the most important and most misunderstood ideas in all of modern physics. It is called the Heisenberg Uncertainty Principle, and it does not mean what most people think it means. The popular version of the uncertainty principle goes something like this. If you try to measure a particle very precisely, the act of measuring it disturbs it, and so you inevitably introduce error into your result. The measurement itself is the problem. If you could only find a gentler way to look, you could know everything you wanted to know. This interpretation is understandable, but it is not correct. The uncertainty principle is not a statement about the limitations of measurement equipment. It is not about the clumsiness of observers or the disturbance caused by probing instruments. It is a statement about nature itself. It describes a fundamental feature of reality at the smallest scales, a feature that exists whether anyone is measuring anything or not. What the principle actually says is this: certain pairs of physical properties are linked in such a way that the more precisely one of them is defined, the less precisely the other can be defined. The most famous of these pairs is position and momentum. A particle that has a very well-defined position, one that is pinned down to a precise location in space, must have a deeply uncertain momentum. And a particle with a very well-defined momentum must be spread across a wide and uncertain range of positions. This is not a measurement problem. It is a description of what the particle actually is at any given moment. the same relationship holds between another important pair of properties, energy and time. If you want to know the energy of a system with great precision, you must observe it over a long period of time. If you can only observe it for a very short interval, the energy becomes correspondingly uncertain. Again, this is not an artifact of imperfect instruments. It is written into the mathematics of quantum mechanics at the deepest level, and every experiment ever designed to test it has confirmed it without exception. This energy-time uncertainty is the key to understanding the quantum vacuum. Consider a region of space that has been emptied of everything, every atom, every photon, every particle of any kind. Classical physics would say that the energy of this region is exactly zero, and that it stays at zero indefinitely, because there is nothing there to carry any energy. But quantum mechanics says something different. If the energy of a region is exactly zero and stays at exactly zero, then it is perfectly known at every moment in time. And a perfectly known energy, held constant over time, violates the uncertainty principle. Nature, at the quantum level, does not permit this. A region of space cannot have a perfectly defined energy of zero any more than a particle can have a perfectly defined position and momentum simultaneously. The energy of even the emptiest region must fluctuate. It must vary randomly and continuously around some baseline value. These fluctuations are not caused by anything entering the region from outside. They are not the result of stray particles drifting in. They are intrinsic to the nature of space itself, a consequence of the same mathematical structure that governs the behavior of every particle and every wave in the universe. This is what physicists mean when they speak of vacuum fluctuations. They are not a poetic metaphor or a loose approximation. They are a precise prediction of quantum field theory, confirmed by multiple independent lines of experimental evidence. The vacuum fluctuates because the uncertainty principle requires it to. There is no way around this, no regime in which the fluctuations go away, no temperature cold enough and no volume small enough to make them stop. It is worth pausing here to let that settle, because it is genuinely remarkable. The universe has a rule that forbids perfect stillness. Even in the complete absence of matter and energy, even in a region that has been evacuated to the greatest degree physically possible, the underlying fabric of space continues to vary. It cannot do otherwise. The rules of quantum mechanics make absolute emptiness not just rare or difficult to achieve, but fundamentally impossible. The uncertainty principle was first described by the German physicist Werner Heisenberg in 1927, and it transformed the way physicists thought about the nature of reality. It shifted the foundation of physics from a world of definite values and precise trajectories to a world of probabilities, distributions, and irreducible uncertainty. And one of its deepest consequences, one that Heisenberg himself may not have fully anticipated, was that it filled the vacuum with something. That something has a name. It is called the zero-point energy, and it is one of the most consequential and most debated quantities in modern physics. Chapter 4. Zero-point energy. The term zero-point energy refers to the lowest possible energy that a quantum system can possess. It is not zero. That is the entire point. In classical physics, the minimum energy of any system is straightforward to define. A pendulum that has been brought to rest, a spring that has been returned to its natural length, a molecule that has been cooled to the point where all thermal motion has ceased. In classical terms, these systems have reached their ground state, and their ground state energy is zero. There is nothing left to remove. The system is, by every classical measure, completely still. Quantum mechanics disagrees. When you apply the mathematics of quantum theory to any system, a vibrating molecule, an electron in an atom, or a region of empty space, the lowest energy state the system can occupy is not zero. It is always slightly above zero, by an amount determined by the uncertainty principle. Even at absolute zero temperature, even in the most perfectly isolated system imaginable, a residual energy remains. This is the zero-point energy, and it cannot be extracted, circumvented, or eliminated. It is the baseline hum of existence itself. The reason for this is directly connected to what was described in the previous chapter. If a quantum system were to reach exactly zero energy and remain there, its energy would be perfectly known and perfectly constant. The uncertainty principle forbids this. The system must retain some minimum level of energetic uncertainty, some irreducible fluctuation around the ground state. The zero-point energy is the mathematical expression of that requirement. For a simple system like a single vibrating particle, the zero-point energy is a small but well-defined quantity. Physicists can calculate it precisely, and experiments confirm those calculations to a high degree of accuracy. The zero-point energy of molecular bonds, for example, has measurable effects on the behavior of molecules at low temperatures, and these effects match the quantum mechanical predictions with impressive precision. When the same reasoning is applied to empty space, however, the results become considerably more difficult to interpret. Empty space, in the framework of quantum field theory, is not truly empty at all. It is better described as a collection of quantum fields, one for each type of particle that exists in nature. Each of these fields permeates all of space, and each of them has its own zero-point energy. When you sum up the contributions of all these fields across all of space, the total is not small. In fact, the naive calculation produces a result that is not just large, but infinitely large. This is a problem that physicists have been grappling with for decades. The infinite vacuum energy is one of the most stubborn puzzles in theoretical physics, and various mathematical techniques have been developed to manage it. To subtract away the infinite parts and work with the finite remainders. These techniques, while mathematically useful, do not fully resolve the conceptual difficulty. The question of why the vacuum energy has the value it appears to have, and what role it plays in the structure of the universe, remains one of the deepest open questions in all of science. What physicists can say with confidence is this: the zero-point energy is real. It is not a mathematical artifact that disappears when the theory is made more rigorous. It shows up in experiments. It produces measurable effects in the physical world. And the most famous of those effects was first predicted in 1948 by a Dutch physicist named Casimir, who realized that two uncharged metal plates placed very close together in a vacuum would experience a force pushing them toward each other. A force produced by nothing more than the energy of empty space itself. The Casimir effect, as it came to be known, was a striking prediction. Two plates, carrying no electric charge, separated by a tiny gap containing no matter of any kind, should nonetheless attract each other because of what the vacuum between them was doing. The force would be extremely small at ordinary distances, but it would increase sharply as the plates were brought closer together, and it would be measurable with sufficiently precise instruments. For several decades after Casimir's prediction, the experimental tools needed to test it with real precision did not exist. The force was so small at accessible distances that confirming it required measurement capabilities beyond what was available at the time. It was not until 1997 that physicist Steve Lamoureux published a careful experimental measurement of the Casimir force that confirmed the prediction to within a few percent. Subsequent experiments have refined that agreement further. The Casimir effect is now one of the best confirmed predictions of quantum field theory, and it stands as direct physical evidence that the zero-point energy of the vacuum is not an abstraction. It pushes things. This is a remarkable thing to sit with. Two metal plates in a vacuum, touching nothing, connected to nothing, carrying no charge and containing no particles in the space between them. And yet, they are drawn toward each other by the activity of empty space. The vacuum reaches out and acts on the physical world because the vacuum is not empty and because the energy it contains is real enough to exert a force. Chapter 5. Fields that fill everything. To understand the quantum vacuum more deeply, it helps to step back from the idea of particles for a moment and think instead about fields. This is a shift in perspective that modern physics made gradually over the course of the 20th century, and it changed the way physicists understood not just empty space, but the nature of matter and energy themselves. In everyday experience, a field is a region in which some influence is felt. The gravitational field of the Earth extends outward into space, growing weaker with distance, but never entirely disappearing. The magnetic field around a magnet fills the surrounding volume, directing compass needles and attracting iron filings into elegant curved patterns. These are familiar examples of fields as regions of influence, invisible structures that exist in space and produce effects on objects that enter them. Quantum field theory takes this concept and extends it in a profound direction. In this framework, every fundamental particle in nature is not a small solid object moving through space. It is instead a localized disturbance in an underlying field. The electron is a ripple in the electron field. The photon, the particle of light, is a ripple in the electromagnetic field. Every type of particle that exists corresponds to a field that permeates all of space, and particles themselves are nothing more than excited states of those fields, regions where the field has been given enough energy to produce what we recognize as a distinct and detectable object. This reframing has enormous consequences for the vacuum. If particles are excitations of fields, then the vacuum, the state with no particles, is not the absence of fields. The fields are still there. Every field that exists in nature is present everywhere in space, at every moment, regardless of whether any particles are moving through it. The vacuum is the state in which all of these fields are sitting at their lowest possible energy level. It is the ground state of all the fields simultaneously. And as the previous chapters have established, the ground state of a quantum system is never perfectly still. Each field, sitting in its ground state, continues to fluctuate. It ripples and stirs at the quantum level, producing temporary disturbances that appear and vanish on timescales too short to be directly observed. These are the vacuum fluctuations described earlier, but understood now in a more complete way. They are not mysterious disturbances in an otherwise featureless void. They are the natural, unavoidable behavior of quantum fields that permeate all of space and cannot be switched off. The number of fields involved is considerable. The standard model of particle physics, the most complete and most precisely tested theory of fundamental particles and forces that currently exists, describes a collection of fields whose interactions account for all known matter and all known forces except gravity. There is a field for electrons, a field for each type of quark, fields for the particles that carry the weak and strong nuclear forces, the electromagnetic field, and the Higgs field, among others. Each of these fields fills all of space. Each of them has a ground state energy. Each of them fluctuates. The Higgs field deserves particular attention in this context. Unlike the other fields in the Standard Model, the Higgs field does not have a ground state of zero. Its lowest energy configuration is a non-zero value. It settles into what physicists call a non-zero vacuum expectation value. This means that throughout all of space, at every point, the Higgs field has a constant non-zero value even in the complete absence of any Higgs particles. The field is simply there, present and active, contributing to the structure of the vacuum and playing a crucial role in giving mass to other particles. The Higgs boson, detected at the Large Hadron Collider in 2012, was not the field itself, but a ripple in that field, evidence that the field exists and that the vacuum is saturated with its influence. This picture of space as a medium filled with overlapping quantum fields, each humming quietly at its ground state energy, is a long way from the classical image of vacuum as pure absence. It is also a long way from the 19th century ether, even though there is a superficial resemblance. The ether was a single mechanical medium, a substance with physical properties like density and rigidity. Quantum fields are something different in kind. They are not made of anything. They do not have a rest frame. They are not detectable as objects. They are the fundamental constituents of reality, the underlying structure from which particles, forces, and ultimately all observable phenomena emerge. What this means for empty space is that the vacuum is not a background against which physics happens. It is an active participant in physics. It has structure. It has energy. It responds to changes in its environment, and in certain circumstances, it can change its own configuration in ways that have dramatic consequences for the universe as a whole. Chapter 6. Virtual Particles. One of the most frequently discussed and most frequently misunderstood consequences of vacuum fluctuations is the concept of virtual particles. They appear in popular explanations of quantum physics with remarkable regularity, and they are almost always described in a way that is at least partially misleading. It is worth taking the time to understand what they actually are, because the reality is stranger and more interesting than the simplified version. The simplified version goes like this. Empty space is constantly producing pairs of particles and antiparticles out of nothing. These pairs appear spontaneously, exist for a brief moment, and then annihilate each other and disappear. They are called virtual particles because they cannot be directly detected. They vanish too quickly to be observed. But while they exist, they have real effects on the physical world. This description is not entirely wrong, but it is not quite right either. Virtual particles are not particles in the ordinary sense. They are not tiny objects that pop into existence, travel a short distance, and then disappear. They are a mathematical tool, a way of organizing and visualizing the calculations that quantum field theory uses to describe how fields interact with each other and with real particles. In quantum field theory, interactions between particles are calculated using a technique developed largely by the American physicist Richard Feynman in the 1940s. The technique involves summing up contributions from all the possible ways an interaction could occur, including ways that would be forbidden by classical energy conservation if they persisted for long enough. These contributions are represented by diagrams, now universally called Feynman diagrams, in which lines represent particles and vertices represent interactions. Some of the lines in these diagrams represent particles that never appear in the initial or final state of the calculation. They exist only inside the diagram, as intermediate steps in the mathematical process. These internal lines are the virtual particles. Because they exist only inside the calculation, virtual particles are not constrained to obey all the same rules as real particles. A real electron must have a specific mass and must carry energy and momentum in a way that satisfies the equations of special relativity. A virtual electron, appearing as an internal line in a Feynman diagram, does not need to satisfy these constraints. It can have the wrong mass, the wrong energy, or the wrong relationship between energy and momentum. This is sometimes described by saying that virtual particles are off-shell, meaning they do not sit on the mathematical surface that defines real, observable particles. This freedom from the normal rules is precisely what allows virtual particles to mediate forces. The electromagnetic repulsion between two electrons, for example, is described in quantum field theory as an exchange of virtual photons. No real photon is emitted and absorbed. If it were, energy and momentum conservation would require the electrons to recoil in specific ways that do not match what is actually observed. Instead, a virtual photon, an internal line in the Feynman diagram, unconstrained by the usual rules, carries momentum between the electrons and produces the repulsive force. This is not a physical process that happens in time. It is a term in a mathematical sum, but the sum correctly predicts the behavior of the electrons, and that is what matters. With all of this in mind, it becomes possible to understand vacuum fluctuations in a more precise way. When physicists say that the vacuum is filled with virtual particles, they mean that the quantum fields permeating space are in a ground state that is not perfectly still, and that the mathematical description of this ground state involves contributions from terms that look like particle-antiparticle pairs appearing and disappearing. These terms are real contributions to the energy and behavior of the vacuum. They have measurable consequences, as the Casimir effect demonstrates, but they are not a population of short-lived objects zipping around in empty space. They are a feature of the mathematical structure of quantum field theory, and interpreting them too literally leads to confusion. What is not confusing is the physical reality that underlies the mathematics. The vacuum fluctuates. The fields that fill space are never perfectly still, and those fluctuations interact with real particles in ways that produce measurable, precisely calculated effects. The anomalous magnetic moment of the electron, a property of the electron that has been measured to extraordinary precision and that matches the predictions of quantum electrodynamics to more decimal places than almost any other quantity in science, depends on contributions from virtual particles in the vacuum. Without accounting for those contributions, the calculation gives the wrong answer. With them, it gives the right one. The vacuum, in other words, is not merely a philosophical curiosity or an abstract theoretical construct. It is a physical environment that participates in the behavior of every particle in the universe. Every electron that has ever existed has been shaped in a small but precisely calculable way by the fluctuating fields of the vacuum it moves through. The emptiness around each particle is not passive, it pushes back. Chapter 7. The Cosmological Constant. There is a number at the heart of modern cosmology that has caused more confusion, more debate, and more genuine scientific discomfort than almost any other quantity in physics. It is called the cosmological constant, and its story connects the quantum vacuum directly to the largest scales in the observable universe. The cosmological constant was introduced by Albert Einstein in 1917, 2 years after he completed his general theory of relativity. General relativity described gravity not as a force, but as a curvature of space-time produced by mass and energy. It was a profound and beautiful theory, but when Einstein applied it to the universe as a whole, it produced an unsettling result. The equations predicted that the universe could not be static. It had to be either expanding or contracting. Since the prevailing assumption at the time was that the universe was eternal and unchanging, Einstein added a term to his equations, the cosmological constant, whose purpose was to counteract gravity and hold the universe in a steady state. A little over a decade later, the American astronomer Edwin Hubble published observations showing that distant galaxies were moving away from us, and that the farther away they were, the faster they were receding. The universe was not static, it was expanding. Einstein, by his own account, regarded the introduction of the cosmological constant as the greatest mistake of his career, and he abandoned it. For several decades, the cosmological constant sat quietly in the history of physics. An embarrassing episode, a fudge factor that had been added for the wrong reasons and then discarded. Most physicists assumed its true value was zero, and that some future, deeper theory would explain why. Then, in 1998, two independent teams of astronomers studying distant supernovae made a discovery that overturned that assumption completely. They were using a particular type of exploding star, a type known as a Type 1a supernova, as a standard candle to measure distances across the universe. These supernovae all explode with roughly the same intrinsic brightness, which means that by measuring how bright they appear from Earth, astronomers can calculate how far away they are. When the two teams compared their distance measurements with the recession speeds of the galaxies hosting those supernovae, they found something that nobody had predicted. The expansion of the universe was not slowing down. It was speeding up. The universe is accelerating. Something is causing the expansion of space to increase over time rather than decrease. That something needed a name and a place in the equations, and the cosmological constant, Einstein's discarded fudge factor, was quietly retrieved from the shelf and put back to work. Today, it is interpreted not as a mathematical convenience, but as a physical reality, a form of energy that fills all of space uniformly, exerts a repulsive effect on the large-scale structure of the universe, and drives the accelerating expansion that the supernova observations revealed. This energy is called dark energy, and it constitutes roughly 68% of the total energy content of the observable universe. It is the dominant component of the cosmos, and its most natural candidate, in the framework of quantum field theory, is the zero-point energy of the vacuum. Here is where the discomfort begins. When physicists calculate the vacuum energy predicted by quantum field theory and compare it to the value of the cosmological constant inferred from astronomical observations, the two numbers do not agree. They do not disagree by a small amount, or even by an order of magnitude. They disagree by approximately 120 orders of magnitude. The theoretical prediction is larger than the observed value by a factor of 10 raised to the power of 120. This discrepancy is widely regarded as the largest single error in the history of theoretical physics. It is sometimes called the cosmological constant problem, and it has resisted solution for decades. No one knows why the vacuum energy is so much smaller than quantum field theory predicts it should be. No mechanism has been identified that would cancel out almost all of the theoretical vacuum energy and leave only the tiny residual amount that astronomical observations require. The problem sits at the intersection of quantum mechanics and general relativity, the two most successful theories in the history of physics, and it may require a synthesis of those two theories to resolve. What the cosmological constant problem makes clear is that the vacuum is not just a curiosity at the particle physics scale. It is connected, in ways that are not yet fully understood, to the structure and fate of the universe at the larger scales. the restless energy of empty space, the same energy that produces the Casimir force between two metal plates in a laboratory, is also, in some form, the energy that is pulling the universe apart. Chapter 8. Phase Transitions in the Vacuum. The vacuum, as the previous chapters have established, is not a fixed and unchanging thing. It is a physical environment with its own energy, its own structure, and its own properties. And like other physical environments, it is capable of changing. The ground state of the quantum fields that fill space is not necessarily permanent. Under the right conditions, the vacuum can shift from one configuration to another, a process that physicists call a vacuum phase transition, and one that has implications so large they are difficult to fully absorb. The concept of a phase transition is familiar from everyday experience. Water, when cooled below a certain temperature, changes from a liquid to a solid. The individual water molecules do not change their composition, but the way they are arranged relative to each other shifts dramatically. The system finds a new configuration of lower energy, and the transition between the two states releases energy in the process. The new phase, ice, has different properties from the old one. It is harder, less fluid, and structured in ways that liquid water is not. Phase transitions in the vacuum work on the same basic principle, but the consequences operate at a scale that makes freezing water seem trivial by comparison. In the early universe, when temperatures were incomprehensibly high and the energy density of space was enormous, the quantum fields that now fill space were in different configurations than they occupy today. As the universe cooled and expanded, those fields settled into lower energy states, much as water settles into ice when the temperature drops below freezing. These transitions change the fundamental properties of space itself. The most consequential of these early vacuum phase transitions is associated with the Higgs field. In the first moments after the Big Bang, the Higgs field is thought to have been in a high-energy symmetric state, one in which all the fundamental particles were massless. As the universe cooled, the Higgs field underwent a phase transition and settled into its current ground state, a non-zero value that permeates all of space. This transition broke the symmetry of the early universe and gave mass to the particles that interact with the Higgs field. Without this transition, electrons and quarks would have no mass, atoms could not form, and the universe as we know it could not exist. This means that the matter-filled structured universe we inhabit is a consequence of a particular configuration of the vacuum. The properties of the particles that make up everything we can see and touch are not intrinsic to those particles in isolation. They are properties that emerge from the interaction of those particles with the current state of the vacuum. In a very real sense, the vacuum does not just surround matter, it shapes it. This raises a question that physicists take seriously. Is the current configuration of the vacuum the lowest possible energy state, or is it merely a local minimum? A stable configuration that could, under the right conditions, tunnel into a different and lower energy state. This is not an abstract theoretical question. It has a concrete answer that depends on the precise values of certain fundamental constants, particularly the mass of the Higgs boson and the mass of the top quark. Calculations performed after the discovery of the Higgs boson in 2012 suggest that the current vacuum state of the universe may be metastable. This means it is stable enough to persist for an extremely long time, far longer than the current age of the universe. But it is not the absolute lowest energy configuration available. There may be a deeper vacuum state, one of lower energy, into which our vacuum could in principle decay. If such a decay were to occur, it would begin at a single point in space where a quantum fluctuation happened to push the local vacuum over the energy barrier, separating the two states. From that point, a bubble of new vacuum would expand outward at the speed of light. Inside the bubble, the values of the fundamental constants, the masses of particles, the strengths of forces, the rules that govern chemistry and nuclear physics, and everything built upon them, would be different, not slightly different, completely different, in ways that would bear no resemblance to the physics of our current universe. The bubble wall would expand at the speed of light. There would be no warning. The region of new vacuum would not announce its arrival in advance, because nothing travels faster than the boundary itself. Any observers in its path would have no knowledge of it until the moment it arrived, at which point the physical laws governing their existence would change instantaneously and completely. This prospect is sometimes called vacuum decay, and while it is genuinely possible in principle, it should not be a source of alarm. The timescale on which such an event would be expected to occur, given current calculations, is vastly longer than the current age of the universe. The vacuum has been stable for nearly 14 billion years, and the probability of a spontaneous decay in any given region of space in any given human lifetime is extraordinarily small. It is a feature of the physics worth understanding, but not a practical concern. What it illustrates, however, is something genuinely profound. The vacuum is not merely a passive background. It has a history, a structure, and a future. It has already transitioned once in ways that made our existence possible. It may transition again in ways that would make our existence impossible. The emptiness that surrounds every atom in the universe is not nothing. It is, in a deep sense, the most consequential thing there is. Chapter 9. The Expanding Vacuum. There is one more dimension to the story of empty space that brings together everything covered so far and places it in the broadest possible context. It concerns the expansion of the universe itself, not just the fact that the universe is expanding, but what that expansion means for the vacuum, and what the vacuum means for the expansion. When Edwin Hubble confirmed in 1929 that distant galaxies were receding from us, and that the farther away they were, the faster they moved, the natural interpretation was that the universe had originated in an extremely dense and hot state and had been expanding ever since. This picture, now known as the Big Bang model, has been confirmed by decades of observation and has become the foundation of modern cosmology. But the expansion it describes is not simply matter flying outward through a pre-existing empty space. It is space itself that is expanding. The vacuum between galaxies is growing. New space is being created continuously, and the galaxies are carried apart by that creation rather than moving through a fixed background. This distinction matters enormously when thinking about the vacuum energy. If the vacuum has a fixed energy density, a certain amount of energy per unit volume, and if the volume of the universe is increasing, then the total vacuum energy in the universe is not conserved. As space expands and new vacuum is created, the total energy associated with that vacuum increases. This is deeply strange from the perspective of classical physics, where energy conservation is a foundational principle. In the context of general relativity and an expanding universe, the situation is more subtle, and the usual rules of energy conservation do not apply in the same straightforward way. What the expansion does to the vacuum depends on the nature of the vacuum energy. If the cosmological constant represents a true and fixed property of empty space, a constant energy density that does not dilute as the universe expands, then as the universe grows larger, the vacuum energy becomes an increasingly dominant component of the total energy budget. Matter and radiation, by contrast, do dilute as space expands. The energy of radiation decreases as the universe expands because the wavelengths of photons are stretched. The density of matter decreases because the same amount of matter occupies a larger volume. The vacuum energy, if it is truly constant, does neither of these things. It simply remains, filling every new increment of space with the same energy density it has always had. This is precisely the behavior that astronomical observations suggest. As the universe has expanded over its 14 billion year history, matter and radiation have become increasingly dilute, while the vacuum energy has remained constant. In the early universe, matter dominated. The expansion was slowing down under the mutual gravitational attraction of all the matter and radiation filling space. But as matter diluted and the vacuum energy remained constant, there came a point, roughly 5 or 6 billion years ago, when the vacuum energy became the dominant term in the cosmic energy budget. After that point, the repulsive effect of the vacuum energy began to outweigh the attractive effect of gravity, and the expansion of the universe began to accelerate. That acceleration has continued ever since, and the observations of distant supernovae that revealed it in 1998 earned their discoverers the Nobel Prize in Physics in 2011. The universe we inhabit today is therefore one in which empty space is winning. The galaxies closest to us, those bound to our local group by gravity, will remain our neighbors essentially forever. But galaxies beyond a certain distance are already receding from us faster than light can travel between us and them. They are not moving through space faster than light. Space itself is expanding between us and them at a rate that carries them beyond any possible future contact. Over vast timescales, more and more of the observable universe will cross this boundary and disappear from view, not because it is destroyed, but because the expanding vacuum will have carried it beyond the reach of any signal we could ever send or receive. In the very far future, if the vacuum energy remains constant and the acceleration continues, the universe will approach a state that cosmologists call the de Sitter phase. In this state, the expansion will be so rapid that the observable universe will shrink to a region not much larger than our local group of galaxies. Everything beyond will be permanently and irreversibly beyond the horizon. The universe will not end in any violent or dramatic sense. It will simply become increasingly empty, increasingly cold, and increasingly dark as the vacuum energy drives apart everything that gravity has not already bound together. There is something quietly extraordinary about this picture. The energy of nothing, the restless, fluctuating, irreducible energy of empty space, is the dominant force shaping the large-scale destiny of the universe. It shaped the early universe by providing the conditions for phase transitions that created the particles and forces we know. It shapes the present universe by driving the accelerating expansion that will eventually isolate our galaxy from the rest of the cosmos. And it will shape the far future by determining the ultimate configuration toward which everything tends. The vacuum is not the absence of the story. It is the story. Chapter 10. What Nothing Tells Us. We have come a long way from the simple question that opened this journey. We began with the word nothing, an ancient and seemingly straightforward concept, a word every child understands before they can read, and we have arrived at a picture of reality in which nothing, in any absolute sense, does not exist anywhere in the observable universe and may not exist anywhere at all. This is worth sitting with for a moment before moving further. The conclusion is not a minor technical footnote to our understanding of physics. It is a fundamental revision to one of the oldest and most persistent intuitions human beings have ever held. For most of recorded history, the universe was understood as matter moving through emptiness. The matter was the interesting part. The emptiness was just the stage. What physics discovered over the course of the 20th century is that the stage is not empty, has never been empty, and in some respects is more consequential than the matter moving through it. The quantum vacuum, as we have explored it across these chapters, has several distinct layers of structure and activity. At the most fundamental level, it is filled with quantum fields, one for each type of particle that exists in nature. These fields do not switch off when no particles are present. They simply drop to their ground states and remain there, fluctuating continuously at the level required by the uncertainty principle. The fluctuations are not random noise superimposed on an otherwise calm background. They are the background. They are what empty space is made of, in the deepest sense that phrase can carry. Above this baseline layer of field fluctuations sits the zero-point energy, the irreducible minimum energy that the vacuum must possess, the value below which it cannot be pushed regardless of how completely matter and radiation are removed. This energy is real in the most practical sense. It produces the Casimir force, measurable in laboratories. It contributes to the anomalous magnetic moment of the electron, calculated and confirmed to extraordinary precision. It shapes the behavior of atoms at low temperatures in ways that match theoretical predictions. It is not a theoretical construct awaiting experimental confirmation. It is an experimentally confirmed reality awaiting complete theoretical understanding. Then there is the cosmological constant, the energy density of the vacuum at cosmic scales, the quantity that drives the accelerating expansion of the universe, and that dominates the total energy budget of the cosmos. Its relationship to the zero-point energy calculated from quantum field theory remains one of the deepest unsolved problems in physics. The two quantities should, by the most natural reasoning, be the same. They are not even close. That discrepancy is not just a numerical puzzle. It is a signal that something fundamental about the connection between quantum mechanics and gravity is not yet understood. And underlying all of this is the possibility of vacuum phase transitions, the capacity of the vacuum to change its configuration, to settle into a lower energy state, to alter the fundamental constants and forces that govern all physical processes. The universe has already undergone such transitions, and those transitions produce the physical world we inhabit, the particles we are made of, the forces that hold us together, the chemistry that makes biology possible. All of these are consequences of the particular vacuum state that emerged from the cooling of the early universe. We are, in a very literal sense, children of the vacuum. What does all of this mean for the way we understand reality? It means, first, that the concept of emptiness as pure absence is not just incomplete, but essentially meaningless at the physical level. There is no such thing in our universe as a region of space that contains nothing. Every point in space is threaded by quantum fields. Every point is subject to vacuum fluctuations. Every point participates in the same energetic ground state that fills the cosmos from one end to the other. The vacuum is not the absence of reality. It is a form of reality, perhaps the most fundamental form, the substrate from which everything else emerges. It means, second, that the boundary between something and nothing is far less clear than it appears. A particle, in the framework of quantum field theory, is a localized excitation of a field that already fills all of space. When the particle is created, the field does not bring something into existence from nothing. It reorganizes energy that was already present in the vacuum into a more concentrated and detectable form. When the particle is destroyed, that energy returns to the vacuum. The creation and destruction of particles is not the appearance and disappearance of something against a backdrop of nothing. It is a continuous transformation of energy between different configurations of the same underlying fields. This picture has philosophical implications that extend beyond physics. The intuition that existence is the exception and non-existence is the default. That things need a reason to exist, but emptiness needs no explanation, does not survive contact with quantum field theory. The vacuum is not the natural resting state of reality, waiting to be populated by matter that arrives from somewhere. The vacuum is itself something. It has energy, structure, and dynamics. If anything, the question of why the vacuum has the particular properties it has, why the zero-point energy has the value it does, why the fields that fill space have the masses and coupling constants they have, why the cosmological constant is as small as it is one of the deepest and least answered questions in all of science. We do not yet have a complete theory of the vacuum. We do not know why it has the energy it has. We do not know whether the current vacuum state is stable or metastable. We do not fully understand the relationship between the quantum vacuum and the geometry of spacetime described by general relativity. These are open questions, and they sit at the frontier of theoretical physics. String theory, loop quantum gravity, and other approaches to a unified theory of quantum mechanics and gravity all make different predictions about the nature of the vacuum, and distinguishing between those predictions experimentally is one of the central challenges facing physics in the coming decades. What we do know is enough to be genuinely astonishing. The universe is not made of matter moving through emptiness. It is made of fields, quantum fields that fill all of space, that interact with each other in precise and calculable ways, that fluctuate continuously even in the complete absence of particles, and that collectively constitute the physical fabric of reality. The vacuum is the ground state of those fields. It is not nothing. It has never been nothing. It hums, and in that quiet, persistent hum, in the restless fluctuations of fields that no instrument can see directly and no temperature can silence, is something that feels, if you sit with it long enough, less like absence and more like presence. Not the presence of any particular thing, not matter, not radiation, not any object that can be named or counted, but the presence of the underlying structure of existence itself, the permanent and irreducible activity of a universe that, at its deepest level, does not know how to be still. The space around you right now, between your hands, between the atoms of your body, between the Earth and the Moon, and the most distant galaxy your best telescopes can reach, is filled with this, with fields, with fluctuations, with the zero-point hum of a vacuum that is, in every meaningful sense, alive with something. We came here to look at nothing, and we found that nothing was, all along, everything. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.